In the vast cosmic ocean that surrounds our solar system, something extraordinary has just occurred. Comet 3I/Atlas, an interstellar visitor from beyond the gravitational embrace of our Sun, has entered what scientists are calling an end-state configuration. This isn't just another astronomical observation to file away in the annals of celestial mechanics. This is a front-row seat to one of the universe's most dramatic transformations, a cosmic event that connects us to the very origins of planetary systems across the galaxy. To understand the magnitude of what we're witnessing, we need to step back and appreciate what an interstellar comet actually represents. These objects are cosmic time capsules, ancient relics from the formation of alien star systems, hurled across the interstellar void by gravitational encounters with massive planets or stellar companions. They travel for millions of years through the cold darkness of space, preserving in their frozen cores the chemical signatures of their home systems. When 3I/Atlas entered our solar system, it became only the third confirmed interstellar object ever detected, following the mysterious Oumuamua in 2017 and Comet 2I/Borisov in 2019. But what makes 3I/Atlas particularly fascinating is that we're now watching it undergo a catastrophic transformation. The term end-state configuration sounds clinical, almost sterile, but what it describes is anything but mundane. This comet is essentially dying before our eyes, fragmenting, disintegrating, and redistributing its ancient material across the inner solar system. Every telescope we can point at this object is capturing data that will reshape our understanding of how comets evolve, how they die, and what this means for the broader picture of matter distribution in our galaxy. Let's consider the physics at play here. A comet is not the solid, unchanging ice ball that popular imagination might suggest. It's a complex, dynamic structure, a delicate balance of frozen volatiles, dust, organic compounds, and rocky material held together by gravity and molecular bonds that formed billions of years ago in conditions vastly different from those in our solar system. When a comet approaches the Sun, everything changes. The gentle bath of solar radiation begins to heat its surface, causing sublimation, the direct transition from solid ice to gas without passing through a liquid phase. This process creates the spectacular coma and tail that make comets so visually striking, but it also begins a process of structural weakening. For an interstellar comet like 3I/Atlas, this thermal stress is particularly intense because these objects likely formed in stellar systems with different characteristics than our own. Their internal composition reflects the chemistry of their birth environment, different isotopic ratios, different molecular structures, different thermal properties. All of these factors influence how the comet responds to solar heating. Think of it like taking an organism adapted to one environment and suddenly transplanting it to another. The stresses can be overwhelming. The fragmentation we're observing isn't a simple cracking apart, it's a cascade of interconnected physical processes. As volatile ices sublimate, they create pressure beneath the surface. Gas jets erupt from weak points in the structure, creating rocket-like thrust that can actually alter the comet's trajectory, a phenomenon called non-gravitational acceleration. These jets also carry dust and larger fragments with them, creating a complex debris field around the nucleus. Meanwhile, the temperature gradient between the sunlit side and the dark side creates thermal stresses that can exceed the tensile strength of the material. Centrifugal forces from the comet's rotation add another layer of stress. The result is a perfect storm of mechanical failure. What makes this particularly exciting from a scientific standpoint is that fragmentation events expose fresh material from the comet's interior. Normally, we can only study the surface layers, which have been processed by radiation and micrometeorite impacts over millions or billions of years. But when a comet breaks apart, pristine material from its core becomes accessible to spectroscopic analysis. We can see molecular species that haven't been exposed to space weathering, organic compounds preserved since the formation of the parent star system, isotopic signatures that tell us about nucleosynthesis processes in that distant stellar nursery. The spectroscopic data coming from 3I/Atlas is already revealing surprises. Early observations suggest unusual abundances of certain molecular species compared to comets native to our solar system. This is exactly what we'd hoped to find, chemical fingerprints that reflect a different formation environment, but interpreting this data requires sophisticated modeling. We need to understand not just what molecules are present, but how they interact, how they sublimate at different rates, and how this affects the overall mass loss and fragmentation process. One of the most intriguing aspects of studying interstellar comets is what they tell us about planetary system formation in general. The current paradigm suggests that all planetary systems go through a chaotic early phase where gravitational interactions between massive planets scatter smaller bodies throughout the system. Some of these bodies are ejected entirely, becoming interstellar wanderers. The composition and structure of these ejected objects provides a window into the architecture and evolution of their home systems. By studying 3I/Atlas, we're essentially conducting comparative planetology across light-years of space. Consider the implications for astrobiology. Comets are known to be rich in organic compounds, the carbon-based molecules that form the foundation of life as we know it. Every major impact of a comet on early Earth delivered not just water but also complex organic chemistry. The famous Miller-Urey experiment showed how simple molecules could form amino acids under the right conditions. But comets may have delivered preformed organic complexity directly to planetary surfaces. If 3I/Atlas carries organic compounds with structures reflecting its alien origin, this expands our understanding of the diversity of organic chemistry possible in the universe. It suggests that the seeds of life might have considerable chemical variation depending on where they form. The trajectory of 3I/Atlas through our solar system also provides crucial data for understanding the dynamics of interstellar space. These objects don't travel through a perfect vacuum. The interstellar medium, though incredibly diffuse, still contains gas, dust, and radiation. Over millions of years of travel, these environmental factors alter the surface properties of interstellar objects. When we observe 3I/Atlas fragmenting, we can look for evidence of this processing. Are there surface layers that behave differently than interior material? Are there chemical gradients that reflect long-term exposure to cosmic rays and ultraviolet radiation? Each observation constrains our models of interstellar transport and evolution. The detection and characterization of objects like 3I/Atlas represents a triumph of modern astronomy. These objects are incredibly faint, moving rapidly across the sky, and distinguishable from solar system objects only through careful analysis of their trajectories. It requires coordinated observations from multiple facilities, rapid communication between observatories, and sophisticated software to separate genuine detections from artifacts and false positives. The upcoming Vera C. Rubin Observatory, with its unprecedented survey speed and depth, is expected to detect dozens or even hundreds of interstellar objects over its operational lifetime. Each one will be a unique sample of material from another star system, and events like the fragmentation of 3I/Atlas will provide the richest scientific return. Let's talk about the mechanics of detection and characterization in more detail, because this illustrates just how far astronomy has come in the past few decades. When an unknown object is first detected, it appears as nothing more than a moving dot on astronomical images. The crucial question is, what is its orbit? By measuring its position at multiple times, we can calculate its trajectory through the solar system. Most objects follow elliptical or hyperbolic orbits that are consistent with being gravitationally bound to the Sun, but interstellar objects have hyperbolic excess velocity. They're moving too fast to be bound by solar gravity alone. This is the smoking gun that identifies an interstellar origin. But confirming interstellar origin is just the beginning. The next challenge is characterization. What is this object made of? What is its size, shape, rotation state, composition? Spectroscopy is our primary tool here. By spreading the light from the object into its component wavelengths, we can identify absorption and emission features corresponding to specific molecules and atoms. For comets, we look for signatures of water, carbon monoxide, carbon dioxide, methane, ammonia, and more complex organic molecules. The relative abundances of these species tell us about formation conditions, temperature, pressure, available raw materials. In the case of 3I/Atlas, the fragmentation event is creating a natural experiment in real-time spectroscopy. As different fragments break off, they expose different materials to sunlight. Each fragment might have a slightly different composition or physical state. By tracking individual fragments and comparing their spectra, we can build up a three-dimensional picture of the comet's internal structure. It's like having a cosmic dissection performed before our eyes, revealing the internal anatomy of an alien world. The dynamics of fragmentation also constrain the mechanical properties of the material. How strong is the bond between particles? What is the tensile strength of the ice matrix? How do different materials respond to thermal cycling? These are questions that have direct implications for planetary defense strategies. If we ever need to deflect a potentially hazardous comet, understanding its structural properties will be crucial for determining the most effective intervention method. A loosely bound rubble pile will respond very differently to a kinetic impactor than a monolithic structure. There's also a fascinating connection to the broader picture of galactic ecology. Stars don't form in isolation. They form in clusters and associations, gravitationally bound groups that gradually disperse over hundreds of millions of years. When planetary systems in these clusters undergo their chaotic early evolution, they scatter objects throughout the surrounding space. Some of these objects remain loosely bound to the cluster, creating a shared reservoir of material that multiple systems can draw from. Others escape entirely and become true interstellar wanderers. The composition and trajectory of objects like 3I/Atlas can potentially be traced back to specific stellar populations, helping us understand the history and evolution of different regions of our galaxy. The isotopic composition of 3I/Atlas is particularly important in this context. Isotopes are variants of chemical elements with different numbers of neutrons in their nuclei. The relative abundances of different isotopes are determined by the nuclear processes that created them: fusion in stellar cores, supernova explosions, cosmic ray interactions. Different stellar populations have different isotopic signatures depending on their age and formation environment. By measuring isotopic ratios in 3I/Atlas material, we can potentially identify what kind of stellar environment produced its parent star system. Was it a metal-rich system formed relatively recently, or an ancient metal-poor population from the early galaxy? These measurements are technically challenging because they require extremely high-resolution spectroscopy to separate spectral lines from different isotopes, but the scientific payoff is enormous. We would be doing stellar archaeology from the comfort of our own solar system, studying the products of stars that might be hundreds of light-years away or that might no longer exist at all. The end-state configuration of 3I/Atlas also raises questions about the ultimate fate of the material. As the comet fragments and disintegrates, it creates a debris stream along its orbital path. This material will continue to orbit the Sun, gradually spreading out and mixing with the existing dust population of the inner solar system. Some particles will eventually spiral into the Sun due to the Poynting-Robertson effect, a process where solar radiation pressure and drag from re-radiated heat gradually reduce orbital energy. Others might be ejected from the solar system entirely by planetary encounters, and a tiny fraction might eventually impact Earth or other planets, delivering their cargo of interstellar material to planetary surfaces. This raises a fascinating question: how much of Earth's inventory of water and organic molecules might have originated in other star systems? We know that Earth experienced a late heavy bombardment period in its early history, when comets and asteroids delivered enormous quantities of volatiles to the surface. If even a small fraction of those impactors were interstellar in origin, then Earth's oceans might contain water molecules that once existed in alien star systems. The carbon in our bodies might include atoms that were part of comets formed around stars now long dead. It's a humbling and awe-inspiring thought: we are not just made of star stuff in the Carl Sagan sense, but potentially of material that has traveled between stars. The study of comet fragmentation also connects to one of the biggest questions in planetary science: what determines whether a planetary system ends up with a particular architecture? Why does our solar system have 4 rocky inner planets and 4 gas giants in the outer system, while other systems might have hot Jupiters orbiting close to their stars, or super-Earths that have no analog in our system? The answer lies partly in the dynamics of the protoplanetary disk from which planets form, and comets are crucial tracers of those dynamics. When massive planets form, they gravitationally sculpt the surrounding disk of gas and dust. They open gaps, excite eccentricities in nearby objects, and either accrete material or scatter it to other locations. Comets that get scattered outward might become part of a distant reservoir like our Oort cloud. Those scattered inward might deliver volatiles to the inner planets, and those ejected entirely become interstellar objects. The statistics of these different populations, how many objects end up in each category, and what their properties are, constrains models of planet formation and migration. Current models suggest that planetary systems typically lose a significant fraction of their initial solid material through ejection into interstellar space. This means there should be an enormous population of rogue planets, planetesimals, and comets wandering through the galaxy. Most of these objects are far too faint and too distant to detect directly, but occasionally one passes close enough to our solar system that we can study it in detail. 3I/Atlas is one such opportunity, and its end state configuration is providing data that will feed into the next generation of planetary formation models. There's also a practical aspect to understanding comet fragmentation that relates to space mission design. Several proposed missions aim to rendezvous with and sample interstellar objects. This is enormously challenging because these objects are moving fast and their arrival time is unpredictable. We need to have spacecraft ready to launch on short notice, with enough propulsive capability to match velocity with an object traveling at tens of kilometers per second relative to the Sun. Understanding how these objects behave as they approach the Sun, whether they remain intact or fragment, is crucial for planning such missions. If we're going to invest billions of dollars in a sample return mission, we need to know whether our target will still exist when we get there. The radiation environment around a fragmenting comet is also fascinating from a plasma physics perspective. As gas sublimates from the nucleus, it becomes ionized by solar ultraviolet radiation and by charge exchange with the solar wind. This creates a complex plasma environment with multiple ion species, magnetic field interactions, and wave-particle interactions. The fragmentation event increases the surface area exposed to sunlight, potentially creating a more complex and dynamic plasma environment than would exist around an intact nucleus. Spacecraft instruments designed to study cometary plasma can capture unprecedented data during these fragmentation events, improving our understanding of plasma processes that occur throughout the solar system and beyond. Let's consider the visual appearance of this event. While 3I/Atlas isn't visible to the naked eye, telescope images reveal a spectacular transformation. What might have started as a relatively compact object with a classic cometary appearance, a bright central condensation surrounded by a diffuse coma and perhaps a tail, has evolved into something more complex. Multiple condensations might be visible, each one a separate fragment following its own trajectory. The dust distribution becomes more extended and irregular as different fragments shed material at different rates. The whole system might start to resemble a small cluster of objects rather than a single comet. Amateur astronomers with modest telescopes can sometimes contribute valuable observations of these events, while professional observatories have larger instruments and more sophisticated detectors. They can't monitor objects continuously. The combination of professional and amateur observations creates a more complete picture of how the fragmentation proceeds over time. This kind of collaborative science, where professionals and amateurs work together, is one of the beautiful aspects of modern astronomy. The chemistry occurring in the coma of a fragmenting comet is extraordinarily complex. Simple molecules sublimating from the nucleus are exposed to intense solar ultraviolet radiation, which breaks them apart through a process called photodissociation. Water molecules break into hydroxyl radicals and hydrogen atoms. Carbon dioxide breaks into carbon monoxide and oxygen. These photodissociation products can then undergo further reactions, creating a cascade of chemical transformations. Additionally, solar wind particles and cosmic rays can induce ionization and additional chemical reactions. The result is that the coma contains hundreds of different molecular and ionic species, each with its own distribution and dynamics. Modeling this chemistry requires sophisticated computational tools that track the production, transport, and destruction of each species. These models need to account for the radiation field, the gas dynamics as material expands away from the nucleus, the temperature structure of the coma, and the chemical reaction rates for hundreds of potential pathways. When a comet fragments, these models become even more complex because now we have multiple sources of gas and dust, each potentially with different composition and outgassing rates. Getting these models to match observations requires iterative refinement, but the payoff is a deep understanding of the chemical processes at work. One particularly interesting aspect of comet chemistry is the presence of complex organic molecules. These are carbon-containing molecules with structures more complicated than simple species like methane or carbon monoxide. Examples include aldehydes, ketones, alcohols, nitriles, and even amino acids. The building blocks of proteins, the formation pathways for these molecules are still debated. Some might form in the protoplanetary disk before being incorporated into comet nuclei, others might form within the comet itself through radiation-driven chemistry over millions of years. Still others might form in the coma through gas phase reactions as simpler molecules photodissociate and recombine. The detection of specific organic molecules in 3I/Atlas would be tremendously exciting because it would show us what organic chemistry looks like in a different stellar environment. Do other star systems produce the same suite of organic molecules as our own, or are there systematic differences reflecting different formation conditions? This has profound implications for astrobiology. If organic chemistry is universal, producing similar molecules regardless of local conditions, it suggests that the chemical foundation for life might be common throughout the galaxy. If instead we see significant differences, it tells us that the pathway to life might be more sensitive to initial conditions than we thought. The study of interstellar objects also connects to the search for extraterrestrial intelligence in an indirect way. Advanced technological civilizations might deliberately send objects between star systems, probes designed to explore neighboring systems and report back. The famous Oumuamua object sparked speculation along these lines because of its unusual properties, though the scientific consensus is that it was a natural object, but the principle remains valid, if technological. civilizations exist and engage in interstellar exploration, we might detect their probes as anomalous objects passing through our solar system. Careful characterization of every interstellar object we detect, looking for signs of artificial structure, unusual materials, or non-gravitational accelerations that don't fit cometary outgassing, is worth doing precisely because the discovery of even one artificial object would revolutionize our understanding of our place in the universe. The timing of 3I/Atlas's fragmentation is interesting from a statistical perspective. Most comets that fragment do so relatively close to the Sun, where thermal stresses are highest, but the exact distance at which fragmentation occurs varies widely depending on the comet's structure and composition. By building up statistics on many fragmentation events, we can start to identify patterns. Do comets from certain families or with certain compositions tend to fragment at particular distances? Are there threshold temperatures or solar flux levels that trigger fragmentation? This kind of statistical analysis requires large samples, which is why every observed fragmentation event is valuable. The long-term evolution of the debris from 3I/Atlas is something we can model but not directly observe on human timescales. The material will continue to spread along the comet's orbital path, forming a meteoroid stream. If Earth's orbit happens to intersect this stream in the future, we might experience meteor showers originating from 3I/Atlas. Shooting stars that are literally pieces of another star system burning up in our atmosphere. The probability of this depends on the details of orbital evolution, which is influenced by planetary gravitational perturbations and non-gravitational forces, but it's not impossible, and there might be meteor showers in Earth's future that trace back to interstellar sources. Let me talk about the broader implications for our understanding of solar system formation and evolution. The NICE model, named after the French city where it was developed, proposes that the outer planets of our solar system underwent significant orbital migration early in solar system history. Jupiter moved inward slightly while Saturn, Uranus, and Neptune migrated outward. This migration destabilized the orbits of countless planetesimals in the outer solar system, some of which were ejected into the Oort cloud. Some crashed into the inner planets during the late heavy bombardment, and some were ejected from the solar system entirely. Every planetary system probably goes through similar dynamical evolution, though the details depend on the masses and initial positions of the planets. This means every star system is both losing material to interstellar space and potentially capturing material from other systems. There's a galactic scale exchange of material happening. A cosmic recycling program where the building blocks of one star system become available to others. 3I/Atlas is a physical embodiment of this process. Material that originated in one stellar environment, traveled through interstellar space, and is now interacting with our Sun. The implications for the distribution of life-supporting molecules throughout the galaxy are profound. If comets regularly exchange between star systems, they could potentially spread not just organic molecules but perhaps even microscopic life itself, a process called panspermia. While the survival of living organisms during million-year journeys through the harsh interstellar environment seems unlikely, it's not impossible, especially for hardy extremophiles that can survive intense radiation and freezing temperatures. Even if living organisms don't survive, the organic molecules they leave behind could seed new environments with complex chemistry that accelerates the origin of life on suitable worlds. The nuclear composition of 3I/Atlas material is another frontier. By nuclear, here, I mean the atomic nuclei themselves, their isotopic makeup. Different isotopes of the same element behave almost identically chemically but can be distinguished spectroscopically with sufficient resolution. The D/H ratio, the abundance of deuterium compared to normal hydrogen, is particularly informative. Deuterium was created in the Big Bang and has been gradually depleted over cosmic history through Nuclear reactions in stellar interiors. The D/H ratio in solar system material reflects the composition of the molecular cloud from which the Sun formed. If 3I/Atlas has a significantly different D/H ratio, it indicates formation from material with a different cosmic history, perhaps from a region of the galaxy that had undergone more or less stellar processing before the parent star formed. Other isotopic ratios are equally revealing. The ratio of carbon 13 to carbon 12, nitrogen 15 to nitrogen 14, and oxygen 18 to oxygen 16 all carry information about the nuclear processes that produce these atoms. In our solar system, these ratios are remarkably uniform across most objects, reflecting thorough mixing of material in the protoplanetary disk. But there are subtle variations that trace back to specific processes. For example, some pre-solar grains, microscopic particles that formed around other stars before our solar system existed and were incorporated into meteorites, show wildly anomalous isotopic ratios that identify them as stellar products from specific types of stars, red giants, asymptotic giant branch stars, supernovae, or novae. If we could measure similar isotopic anomalies in 3I/Atlas, we'd be able to reconstruct the nuclear history of its parent system. Did it form from material enriched by a nearby supernova? Was the parent star metal-rich or metal-poor? These questions connect comet science to galactic chemical evolution, the progressive enrichment of the interstellar medium with heavy elements as generations of stars are born, live, and die. The mechanical properties revealed by fragmentation patterns tell us about the formation and evolution of the comet nucleus itself. Current models suggest that comet nuclei are not uniform structures but rather complex aggregates of smaller components. Think of them as cosmic rubble piles, collections of icy pebbles and boulders weakly bound by their mutual gravity and by sintering, a process where ice crystals gradually fuse together under pressure. This structure makes them inherently fragile, susceptible to disruption when stresses exceed the relatively weak bonds holding everything together. The fragmentation sequence of 3I/Atlas might reveal this hierarchical structure. If the nucleus breaks into a few large pieces initially, it suggests there were pre-existing planes of weakness, perhaps boundaries between major structural components that were never fully integrated. If instead it crumbles into many small fragments more or less simultaneously, it suggests a more uniform but generally weak structure throughout. The size distribution of fragments follows power law statistics in many cases, similar to what we see in asteroid families created by catastrophic collisions. Analyzing these distributions helps us understand the fracture mechanics of icy materials under the extreme conditions of the space environment. Temperature plays a crucial role in determining mechanical properties. At very cold temperatures, far from the sun, water ice behaves like rock, hard, brittle, and strong, but as temperature increases, ice begins to soften and becomes more ductile. It can flow slowly over time through a process called creep, where the crystalline structure rearranges under stress. This temperature-dependent behavior means that the mechanical response of a comet nucleus changes as it approaches the Sun. Parts that were strong and rigid in the outer solar system become weak and pliable in the inner system. Combined with thermal expansion stresses and the pressure from sublimating gases, this temperature evolution creates a recipe for mechanical failure. The rotation state of 3I/Atlas adds another layer of complexity. All astronomical bodies rotate, and for small objects like comet nuclei, rotation can create significant centrifugal stress. If a nucleus is rotating rapidly, the equatorial regions experience outward centrifugal force that partially counteracts gravity. For a weakly bound rubble pile structure, there's a maximum rotation rate beyond which centrifugal force exceeds the gravitational and cohesive forces holding the structure together, and the object flies apart. This is called the spin barrier, and we've observed several comets that appear to have fragmented at least partially due to rotational stress. Outgassing can alter rotation rates through the rocket effect I mentioned earlier. Jets of gas carrying dust particles away from the nucleus create thrust, and if these jets are not perfectly symmetric, they create torque that changes the rotation rate and orientation over multiple orbits. This can spin a nucleus up to the point of structural failure, or it can spin it down and stabilize it. The interplay between outgassing torques, structural strength, and rotation rate is a complex dynamical problem that requires detailed modeling of gas flow, dust transport, and nucleus shape. Speaking of shape, the morphology of comet nuclei is remarkably diverse. Spacecraft missions have visited several comets and revealed a menagerie of shapes, some roughly spherical, others highly elongated, still others with distinct lobe structures suggesting they formed from the merger of separate objects. The famous comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft, has a distinctive duck-shaped morphology with two lobes connected by a narrow neck. This almost certainly reflects a low-velocity collision between two separate objects early in solar system history, a gentle merger that left both components largely intact. We don't have close-up images of 3I/Atlas, of course. It's far too distant and faint for current imaging technology to resolve any surface details, but we can infer some characteristics from how light reflects off it, the light curve, the variation in brightness as the nucleus rotates, encodes information about shape and rotation period. A highly elongated object will show larger brightness variations than a nearly spherical one as different cross-sections are presented to the observer. By monitoring the light curve over time and looking for patterns, we can estimate the rotation period and constrain the axis ratio. The color of reflected light also provides clues about surface composition. Cometary surfaces tend to be quite dark, darker than coal in many cases, because organic compounds created by radiation processing of ices create a dark lag deposit on the surface. This material doesn't sublimate readily, so it accumulates as the more volatile ices beneath it escape. The resulting dark crust actually insulates the interior, reducing sublimation rates from covered areas, but where this crust cracks or gets blown off by particularly vigorous outbursts, fresh bright ice becomes exposed and shows up as bright patches in images. The spectrum of sunlight reflected from 3I/Atlas contains absorption features that identify specific minerals and compounds on the surface. Different materials absorb light at characteristic wavelengths determined by their molecular or crystal structure. By comparing observed spectra to laboratory measurements of candidate materials, we can identify likely surface components. This is challenging because surfaces are typically mixtures of many materials, and the spectral features of these components overlap and blend together. Sophisticated unmixing algorithms and extensive spectral libraries of pure materials help us disentangle these complex spectra. One of the key questions about interstellar comets is whether they show significant differences in composition compared to solar system comets. Early observations of 2I/Borisov suggested it was remarkably similar to solar system comets in its gas production and dust-to-gas ratio. This was somewhat surprising. We might have expected alien comets to look obviously different, but it also makes sense from a theoretical perspective. The basic physics and chemistry of planetary system formation should be similar everywhere. Hydrogen and oxygen are the first and third most abundant elements in the universe, so water ice should be ubiquitous. Carbon is the fourth most abundant element, so carbon-bearing molecules should be common. The detailed relative abundances might vary, but the broad picture should be recognizable. However, there are some intriguing hints of differences. The ratio of carbon monoxide to water in 2I/Borisov appeared to be higher than typical solar system comets. though still within the range of variation seen in some rare solar system objects. If 3I/Atlas shows similar or even more pronounced compositional anomalies, it would support the idea that while the basic inventory is similar, the detailed chemistry varies between systems. This variation probably reflects differences in formation, location within the protoplanetary disk, temperature, pressure, and available raw materials all vary with distance from the star, as well as possible differences in the composition of the molecular cloud from which the system formed. The dust produced by comets is as scientifically interesting as the gas. Cometary dust particles are typically fluffy aggregates of smaller grains, with structures that have been compared to soot or to certain types of snowflakes. They contain a mixture of silicate minerals, carbonaceous material, and sometimes tiny inclusions of metal. The size distribution ranges from nanometer-scale particles up to millimeter-sized or larger chunks. Each size range interacts differently with sunlight and carries different information about formation processes. The smallest particles, typically less than a micrometer in size, are blown away from the sun by radiation pressure faster than they can fall inward due to gravity. These particles form the comet's dust tail, which points away from the sun regardless of the comet's direction of motion. Larger particles are less affected by radiation pressure and follow trajectories closer to the comet's orbit, forming a curved dust trail that traces the orbital path, the distribution of particle sizes and their trajectories can be inferred from detailed imaging and modeling of the dust environment. Collecting and analyzing cometary dust particles provides the ultimate ground truth for composition studies. Several spacecraft missions have accomplished this. Stardust collected particles from Comet Wild 2 and returned them to Earth, while Rosetta performed in situ analysis at Comet 67P. These particles revealed incredible complexity, with individual grains showing evidence of high-temperature processing followed by incorporation into cold outer solar system environments. Some grains are clearly pre-solar material that predates the solar system entirely. This mixture of processed and unprocessed material reflects the chaotic environment of the early solar system, where material from different locations and with different thermal histories was mixed together. For an interstellar comet like 3I/Atlas, dust collection would be even more valuable, but also extraordinarily challenging. The high relative velocity of the comet means that even tiny dust grains carry enormous kinetic energy. A micrometer-sized particle hitting a spacecraft at 20 km per second delivers energy comparable to its mass in TNT. Special aerogel collectors like those used by Stardust can capture particles without destroying them, but even these have limitations at very high velocities. Alternative collection strategies might involve deploying large collecting surfaces that allow particles to impact and vaporize, then analyzing the vapor, or using electrical fields to decelerate and trap charged particles. The fragmentation of 3I/Atlas is producing a massive increase in dust production as fresh surface area becomes exposed. This dust will gradually spread throughout the inner solar system, and some fraction will eventually be captured by Earth's atmosphere. Specialized high-altitude aircraft and balloons routinely collect cosmic dust from the stratosphere, and it's possible that some particles from 3I/Atlas might eventually be recovered this way. Identifying such particles would require matching their composition to the spectroscopic signature of 3I/Atlas and showing that they're distinct from typical solar system dust, which is challenging but not impossible with sufficiently sophisticated analytical techniques. Let's consider the broader context of small body populations in the galaxy. Our solar system contains billions of comets in the Oort cloud and Kuiper belt, along with asteroids in the main belt and other regions. Extrapolating from the masses and architectures of observed exoplanetary systems, We can estimate that the galaxy as a whole contains something like 10 to 21 to 10 to 22 small icy bodies in cold storage around their parent stars. A small fraction of these get ejected into interstellar space through gravitational interactions, creating a vast population of rogue objects drifting between the stars. The density of these objects in interstellar space is extremely low, perhaps one object of kilometer size or larger per cubic astronomical unit on average. This means that the distance between neighboring interstellar objects is typically millions of kilometers or more. They're essentially invisible unless one happens to pass close to our solar system where our telescopes can detect it. Current detection rates suggest that 1 to 2 interstellar objects per year pass within Jupiter's orbit close enough for detection, though most of these are probably too faint to discover with current technology. As our survey capabilities improve, particularly with the Vera Rubin Observatory coming online, the detection rate should increase dramatically. We might find tens or hundreds per year, and this will transform interstellar object science from studying individual curiosities to statistical analysis of populations. We'll be able to ask questions like, what is the size distribution? How does composition vary among different objects? Are there distinct families that might trace back to different types of parent systems? Do objects from old stellar populations look systematically different from those from young populations? The kinematics of interstellar objects, their velocities and directions of travel, encode information about galactic structure and dynamics. Stars in the galaxy orbit the galactic center in roughly circular paths, but with some spread in velocities, creating what astronomers call velocity dispersion. Objects ejected from planetary systems inherit the velocity of their parent star plus some additional component from the ejection process. By measuring the velocity distribution of interstellar objects detected passing through our solar system, we can infer properties of the stellar population they came from. There's even the tantalizing possibility of using interstellar objects for precision astrometry. If we could track an object's position very precisely over many years as it travels away from the solar system, deviations from a straight-line path would indicate gravitational perturbations from unseen mass. This could potentially detect rogue planets wandering in interstellar space, or even provide constraints on dark matter properties if dark matter clumps can gravitationally deflect these objects. This is very speculative and would require measurement precision well beyond current capabilities, but it illustrates how interstellar objects might serve as probes of the invisible universe. The end-state configuration of 3I/Atlas raises questions about the ultimate fate of interstellar objects that don't fragment. Some will pass through the solar system and continue on into interstellar space, little changed by their brief encounter with the Sun. Others might fragment completely, distributing their material throughout the inner solar system. A few might even be captured into bound orbits around the Sun through a close gravitational encounter with a planet, though this requires very specific circumstances and is quite rare. Captured interstellar objects would be extremely interesting targets for study because we'd have repeated opportunities to observe them at each perihelion passage. The capture process requires the object to lose enough energy during a planetary encounter that its velocity falls below the solar system escape velocity. This can happen through a three-body interaction where the object approaches a planet that has a moon, and the complex gravitational dance extracts energy from the object's heliocentric orbit. Alternatively, if the object undergoes extreme outgassing or fragmentation during perihelion passage, the associated mass loss can reduce its velocity enough for capture, though this requires losing a significant fraction of the total mass. Some researchers have speculated that certain unusual objects in the solar system might actually be captured interstellar objects. For example, the Centaurs, objects orbiting between Jupiter and Neptune, have dynamical lifetimes much shorter than the age of the solar system. meaning they must be continuously replenished from some source population, while most are probably escapees from the Kuiper belt. Could some fraction be captured interstellar objects? Compositional studies comparing centaurs to known solar system populations might reveal anomalies that support this hypothesis. The study of 3I/Atlas also contributes to our understanding of impact hazards. While the probability of Earth being impacted by an interstellar object is extremely small, it's non-zero, and the consequences could be significant. Interstellar objects approach at high velocity, potentially 40 to 50 kilometers per second or more relative to Earth. At these velocities, even a small object releases enormous energy on impact. A 100-meter diameter object impacting at 50 kilometers per second would release energy equivalent to hundreds of megatons of TNT, enough to cause regional devastation. Fortunately, the low number density of interstellar objects means such impacts should be exceedingly rare on human timescales, but over geological time, Earth has almost certainly been hit by interstellar objects multiple times. Looking for evidence of such impacts in the geological record is challenging because they would be difficult to distinguish from impacts by solar system objects without detailed compositional analysis of impact residue, isotopic anomalies in impact glasses or meteoritic material embedded in crater structures might provide clues, but this is speculative at present. The fragmentation behavior of 3I/Atlas has implications for impact modeling. If interstellar comets are structurally weak and prone to fragmentation, they might break apart in Earth's atmosphere before reaching the ground, potentially spreading their energy over a larger area but reducing the likelihood of a concentrated impact. This is somewhat analogous to the Tunguska event of 1908, where an object, probably a small asteroid or comet, exploded in the atmosphere over Siberia, flattening forests over a large area but not creating a crater. The actual impact risk depends sensitively on the object's structure, composition, entry angle, and velocity, all of which are uncertain for interstellar objects. Let me shift focus to the observational campaign studying 3I/Atlas. Coordinating observations of transient events like comet fragmentation requires rapid communication and collaboration between observatories worldwide. When fragmentation is detected, alerts go out through networks like the Astronomer's Telegram and the Central Bureau for Astronomical Telegrams. Observatories with appropriate capabilities then schedule observations to capture data before the event evolves or the object becomes too faint to study. Different observatories contribute different capabilities. Large telescopes with sensitive spectrographs can detect faint emission lines and absorption features that reveal composition. Wide-field telescopes can monitor the overall structure and search for additional fragments. Radio telescopes can detect molecular emission lines at millimeter wavelengths, providing complementary information about gas production and composition. Space telescopes like Hubble can obtain very high spatial resolution images and ultraviolet spectra not accessible from the ground. The combination of all these data sources creates a comprehensive picture of the fragmentation event. The data reduction and analysis process is substantial. Raw telescope images must be calibrated to remove instrumental signatures, aligned to account for the object's motion across the sky, and processed to extract photometric and spectroscopic information. This requires specialized software and expertise. For spectroscopy, the analysis involves identifying emission and absorption lines, measuring their intensities and wavelengths precisely, and comparing to molecular databases to determine which species are present. Line profiles encode information about velocity fields, gas expansion speed, rotation, and turbulence, which must be carefully modeled. The theoretical interpretation of observations requires sophisticated numerical models. Gas production models simulate how molecules sublimate from the nucleus, expand into the coma, and undergo photodissociation and other chemical reactions. These models must solve coupled equations describing gas dynamics, radiative transfer, and chemistry, often on complex three-dimensional grids. The computational demands are substantial, requiring high-performance computing resources. Matching model predictions to observations allows us to infer properties of the nucleus that we can't measure directly, like its temperature distribution and subsurface composition. Fragmentation events require even more complex modeling because now we have multiple sources of gas and dust, each with potentially different properties and evolution. The fragments themselves might continue to fragment further, creating a cascade of smaller pieces. Tracking individual fragments and modeling their separate contributions to the overall coma is computationally challenging but necessary to extract maximum scientific value from the observations. The formation environment of 3I/Atlas's parent star system is something we can attempt to constrain through compositional analysis. Different regions of protoplanetary disks have different temperatures, and this affects which molecules can condense into solid form. Very close to the star, temperatures are too high for any ices to form, only refractory materials like silicates and metals can condense. Further out, water ice becomes stable. This is called the snow line or ice line. Still further out, more volatile species like carbon dioxide, methane, and nitrogen can condense. The composition of objects reflects the temperature of the region where they formed. In our solar system, the ice line is thought to have been located somewhere between Mars and Jupiter during planet formation. Objects that formed beyond this line are ice-rich, while those that formed inside are rocky and metal-rich. The giant planets formed beyond the ice line where their cores could accrete massive gaseous envelopes thanks to the abundant solid material available. If we can determine the formation location of 3I/Atlas within its parent disk from its composition, we learn about the architecture and thermal structure of that alien planetary system. The organic chemistry preserved in 3I/Atlas connects to one of the most profound questions we can ask: how common is life in the universe? The chemical building blocks of life, amino acids, nucleobases, lipids, can form through abiotic processes in space and be delivered to planetary surfaces by comets and asteroids. If this delivery is efficient and the chemistry is favorable, planets with liquid water might have a head start on the path to life. But if the necessary chemistry is rare or requires very specific conditions, life might be correspondingly rare. We can't determine this from a single comet, of course, but every data point helps. If 3I/Atlas contains amino acids or other prebiotic molecules, it extends the sample of environments where such chemistry occurs. If the relative abundances of different organic molecules show patterns different from solar system comets, it tells us about the range of starting conditions that might lead to life. Building up a library of compositions from multiple interstellar objects from different stellar environments will gradually paint a picture of the diversity of organic chemistry in the galaxy. The energy sources driving chemical reactions in comets are varied. Solar ultraviolet radiation is the obvious one. High-energy photons can break chemical bonds and drive photochemistry, but cosmic rays also play a role, penetrating deep into the comet nucleus and creating reactive species that can trigger chemical reactions even in the dark interior. Radioactive decay of elements like aluminum-26 and iron-60, which were present in the early solar system, can provide heat that drives thermal chemistry. All these processes work over millions of years to gradually modify the composition of cometary material. In an interstellar comet, we're sampling the results of these processes operating in a different stellar environment, potentially with different radiation fields and different abundances of radioactive isotopes. The composition we observe is a palimpsest recording this complex history. Disentangling the various contributions requires comparing observations to models of radiation chemistry. Thermal evolution, and cosmic ray processing under varying conditions. The dust-to-gas ratio in cometary COMI is an important diagnostic of nucleus properties. If the ratio is high, it indicates either that the nucleus has a high dust content or that volatile ices have been depleted, leaving a dust-rich residue. If the ratio is low, it suggests abundant volatile ices relative to dust. For 3I/Atlas. Measuring this ratio and comparing it to solar system comets provides another test of similarities and differences between stellar systems. The fragmentation event might alter the observed dust-to-gas ratio as different materials are preferentially exposed or lost.